Hello, welcome to my channel. I'm Ameya and we are discussing about stability in control systems. Now, stability is a desired quantity or desired characteristics of your control system because a stable system will have some specific pattern by which it will behave or perform. Okay, so there is less change in output as there is change in input. That is what the condition of stability is. So practically all systems are designed to be stable. The unstable systems are unpredictable, so we avoid designing unstable systems. If my system is unstable, I try to control that system to become a stable system. Okay, and in that case, stability is an important thing, and we need to understand how system stability can be found out and how to understand various conditions of the stability. So that is what your stability is, and most of the time, stability derives or comes from the characteristic equation. So we have seen the closed loop transfer function will be something like g of s upon 1 plus g of s into h of s. So most of the time the stability conditions will be coming from this characteristic equation. The denominator of your function is basically a characteristic equation, and from these characteristic equation, the first stability necessary conditions for stability we are going to understand. Let us assume a characteristic equation delta s is equal to an is my coefficient, s raised to n is my starting coefficient of s, and I am continuing with some unknowns, that is an minus 1 s raised to n minus 1. This should come in denominator, just a second, plus and so on till a1 s plus a0 is equal to 0. So this is basically a denominator of your transfer function that is considered as a characteristic equation, and then we have to follow two conditions, necessary conditions for stability, that all coefficient of the characteristic equation must exist. Okay, so there should not be any zero in our coefficients, and all coefficients must be positive also. These are the very important conditions, but these are necessary but not sufficient conditions. Let us understand this. Let us take an example: s square plus 4s plus 3. This is one of my characteristic equation. I can check with all conditions, all coefficient must be exist. S square coefficient is there, s coefficient is there, and s raised to 0 coefficient is there. This is what all coefficients must exist condition is, and all coefficient must be positive. So that is 1 positive, 4 is positive, and 3 is positive. So this system is going to be stable, or this is not going to be surely unstable. Okay. So if I give a case of s raised to 4 minus 3s square plus 2 s plus 3, in this case the s cube is missing here, s cube is missing. So this first condition is not satisfied. That means system is surely going to be unstable. Okay, similarly all coefficients must be positive. Even though s cube is there, this minus sign will make my system unstable. Okay, so this is how these are the necessary but not sufficient conditions. So even though these both conditions are satisfied, that all coefficients are there in my system and all coefficients are positive, still your system can be unstable. But these are the necessary condition to check the stability. If any of the condition is not satisfied, your system is going to be definitely unstable. Okay, so these are that is what the necessary conditions for stability is. We just need to check whether these two conditions are valid or not, and then you can go for the first method by which we can find the stability, that is the Routh's criteria. Again, this Routh's criteria is dependent on your characteristic equation. So first we need to find the characteristic equation and then arrange those coefficients in the term called Routh's array. Okay, so what is this Routh's array? It's very simple. If I have the equation s raised to n a n plus a n minus 1 s raised to n minus 1 and so on till a1s plus a0 s raised to 0, I can arrange this equation starting with this first factor s raised to n. So first row of my array will be s raised to n and it will cover all even coefficients. Even coefficients as in skipping one coefficient every time. So this will be a n, the second will be a n minus 2, a n minus 4 and so on. The second row will be a n raised to minus 1, that is the second coefficient, and it will jump to odd coefficients. Okay, so this will be a n minus 1, this is a n minus 3 and so on, it will be till the end of my coefficients. Now what about s raised to n minus 2? This will be b1 where b1 is equal to the first value an minus 1, the second value determinant of these four. So it will be minus determinant an minus 1, an minus 2 and an minus 3 divide by the above value, which is an minus 1. Similarly, you can have b1, sorry b2, not b1, where b2 will be minus determinant. In the case of b2, you have to consider the first row first column, and skipping the second column you can go with an minus 1, first column will be always there, an minus 4, skipping the second column, an minus 5 divide by an minus 1. Okay, this one. So this is how your b1 and b2 will go. Then you have s raised to n minus 3. You can find c1 using this b1 and these figures similarly, and this will continue till s raised to 0. Okay, so you will get some value of zn. Okay, and remember, this is not the perfect array, this is the reducing array. So every time your term will keep on decreasing and finally you will get only one value for s is equal to 0. So how many number of rows will be there, that depends on your characteristic equation. How many number of terms you have in your characteristic equation, that many number of rows will be definitely there in your Routh's array. Now the question is why we are doing this. So how my stability affects. So the condition for stability in Routh's array will be considering the first column. If there is a sign change in my first column, that means system is going to be unstable. If there is no sign change, in the all terms of the first column, that system is going to be stable. This is how you can predict stability using Routh's stability criteria. So first we have to create this array, then we have to check whether there is a sign change. Sign change is basically from plus to minus, that is the sign change. Okay, so we need to find whether this sign change is there or not, and if there is a sign change, system is going to be unstable. If there is no sign change, system is going to be stable. That is how we can comment on stability of your Routh's array. Okay, so in coming videos we will discuss about various conditions of Routh's array, starting with first case, that is the simple Routh's array, and how we can calculate stability or understand stability using Routh stability criteria. If you like this content, do subscribe my channel, share it with your friends, and do check the playlist which are available on my channel about the control systems, mechanical measurements and automation. Thank you for joining.